In October 2022, during the Orionids meteor shower, a fireball was captured on camera in North America. Other meteors left long streaks of glowing debris in the sky. A little earlier, in March 2022, an asteroid crashed into Earth's atmosphere and was captured by one of the meteorological satellites. Fortunately, the asteroid, named 2022 EB5, was only 2 meters (6.5 feet) wide, so it didn't result in a catastrophe. But not all cosmic collisions are so safe. Some of them are powerful enough to damage planets or even lead to their destruction. What explosion captured on camera is hundreds of times the power of our entire nuclear arsenal. Which cosmic explosion left a void the size of many galaxies around it? And what single meteorite triggered the creation of an Earth defense program? Scientists often observe cosmic calamities. And in 1993, they were preparing to watch the comet Shoemaker-Levy 9 SL9 crash into Jupiter by 1994. But at the very last moment, it turned out that the collision would occur on the night side of Jupiter, and the initial impact wouldn't be visible from Earth. Only NASA's Galileo spacecraft, which was on its way to the gas planet, had a front-row seat for the spectacle. The space probe captured the comet entering Jupiter's atmosphere at about 60 kilometers per second, 37 miles per second. With 1-second intervals, Galileo took a series of images showing the appearance of a fireball and recorded its peak temperature of 23,700 degrees Celsius, 42,700 degrees Fahrenheit. Soon Jupiter, which makes a complete rotation on its axis in just 10 hours, allowed this fireball to be seen from Earth. Then NASA's infrared telescope captured a fragment of SL9 that was still rising above the edge of the planet after the initial impact on the night side of Jupiter. But the best images were made by the Hubble telescope using a high-resolution camera. The telescope was broadcasting at least once a day for a week. Slowly, as the planet rotated, it showed dark spots on Jupiter left from the impact of the comet fragments. The Hubble Space Telescope has recorded the collision of 21 SL9 fragments with the gas giant. The image showed fragments of the comet stretching nearly 1,140 kilometers, 710,000 miles, which is about 3 times the distance from Earth to the Moon. Other observatories and telescopes also kept a constant watch. The largest impact was caused by a huge fragment of a comet named Fragment G. The result was a giant dark spot on the surface of the planet, more than 12,000 kilometers, 7,500 miles across. This is almost the diameter of the entire Earth. According to some estimates, the explosion released energy equivalent to 6 million megatons of TNT. At the time, this was 600 times the explosive power of the entire nuclear arsenal of the world. Meanwhile, the impacts continued. At an interval of 12 hours, 2 more explosions followed, leaving trails almost as large as the G fragment left. The collision sent gigantic plumes of debris flying into space, rising 3,000 kilometers, 1,900 miles, above the cloud tops. A few minutes later, they plummeted back to the planet's surface, turning it again into a blazing furnace of flames. In addition, the collisions generated huge waves of energy that swept across Jupiter at 450 meters per second, 1,476 feet per second. The spots from this impact were visible on the surface of the gas giant for many months, and some were even more noticeable than the famous Great Red Spot. But regardless of how big the catastrophe was, it provided astronomers with many valuable insights. When debris from the comet crashed into Jupiter, scientists had a momentary window to look into the gas giant's atmosphere. Material from the lower layers was ejected into the dense upper clouds, and astronomers learned more about the planet's chemical composition. Researchers found 2-atom sulfur and sulfur carbon, as well as the emission of heavy atoms of iron, magnesium, and silicon. Instruments have also detected a layer of water in the atmosphere, though less significant than expected. Researchers believe that a more water-bearing layer may be hiding deeper in the atmosphere, where the SL9 fragments didn't penetrate. In addition, the shock waves that rushed across the planet after the impact helped track wind movements. And changes in the polar lights on the gas giant showed how the magnetosphere is affected by comet and asteroid particles. The event also made scientists think more about protecting the Earth from such celestial bodies. Most of them, like SL9, are caught by Jupiter's extreme gravity. The frequency of comets and asteroids colliding with Jupiter is believed to be 2,000 to 8,000 times higher than on Earth. Astronomers believe that without this cosmic vacuum cleaner, complex life might not have developed on our planet. But the gas giant cannot keep us safe all the time. Craters from celestial rock impacts exist on the Moon, Mars, Venus, and, of course, Earth. One asteroid impact in the past has already created a huge crater on our planet, causing natural disasters and making the dinosaurs go extinct. And today, dangerous celestial visitors often come by Earth. A huge asteroid flew close to Earth on Halloween 2022. If this potentially hazardous object was placed next to one of the world's tallest skyscrapers, the Burj Khalifa in Dubai, they would be almost equal in size. The Burj Khalifa is 828 meters, 2,716 feet tall, while the maximum estimate for the size of the asteroid, named 2022 RM4, is 740 meters, 2,428 feet, in diameter. This rock mountain was hurtling through space at about 84,500 kilometers per hour, 52,500 miles per hour, and that is about 68 times the speed of sound. The asteroid was captured on camera as part of the Virtual Telescope project in Italy on October 31st. The next day, it flew by 2.3 million kilometers, 1.43 million miles, from Earth. That is about 6 times farther than the average distance from Earth to the Moon, but still very close by cosmic standards. So our solar system is a much more peaceful place than it was 4.5 billion years ago. There's still a lot happening here. Some random celestial rock can one day easily damage Earth, just as SL9 damaged Jupiter. To prevent this possible catastrophe, it was decided to build a reliable line of defense against comets and asteroids. And the first step was the identification of potentially hazardous objects in space. Until the mid-1990s, only a few teams of astronomers were searching for asteroids in the inner solar system. But after the Shoemaker-Levy comet hit Jupiter, we came up with the term planetary defense, and new teams joined the research. Scientists now work together to track near-Earth objects, especially asteroids that come within 48 million kilometers, 30 million miles of Earth's orbit. NASA has already detected 90% of potentially dangerous asteroids that are 1 kilometer or larger. The agency is now working to identify at least 90% of asteroids between 140 to 1,000 meters, 450 to 3,300 feet wide. At the same time, space organizations around the world are looking for ways to deflect orbits of celestial bodies that threaten our planet. In September 2022, the DART spacecraft diverted the asteroid Dimorphos by changing its orbit in the very first test of Earth's defense system. China has also planned a mission to alter the flight of the asteroid 2020 PN1 in 2026. Scientists have also thought about space dangers to the planet on a global scale. Researchers have many times captured extremely powerful explosions in other star systems and galaxies. The outburst in the Ophiuchus galaxy cluster is considered the strongest one captured on camera. The giant flash was captured by several telescopes. The explosion was so powerful that it punched a cavity the size of 15 Milky Way galaxies placed in a row in the plasma cluster surrounding a black hole. It all happened very far away, about 390 million light-years from Earth. This eruption of unprecedented power gave us stunning images, and scientists received an opportunity to study this grand event using data from NASA's Chandra X-ray Observatory, ESA's XMM Newton, the Murchison Wide Field Array, and the Giant Meter Wave Radio Telescope. But in October 2022, NASA recorded an explosion in the universe that reached our planet. Astronomers believe it was caused by the birth of a black hole at the center of a supernova 1.9 billion years ago in the constellation Sagitta. The explosion released the gamma-ray burst, GRB 221009A, and a wave of X-rays and gamma rays reached the solar system, sweeping through it. The detectors on the Fermi and Swift space telescopes were triggered by this event. Fermi recorded gamma-ray energy data, detecting photons with energies of more than 100 million electron volts. By comparison, photons of visible light have energies of about 2 electron volts. The Swift X-ray telescope captured the afterglow of the gamma-ray burst about an hour after it was first detected. The bright rings on it are visible as a result of X-rays scattering among layers of dust in our galaxy. But the gamma-ray burst didn't do any harm to our planet this time either. Its epicenter was too far away, and only a tiny fraction of the radiation reached Earth. Had it happened closer to us, the Earth might have been in trouble. A supernova explosion is one of nature's most powerful forces. It can generate as much energy as the sun will create in its lifetime. Such a flood of gamma rays has incredible destructive power. On Earth, it would vaporize the atmosphere and turn all living beings into ash. And researchers believe our planet has experienced something like this at least once in the past. According to NASA, about 445 million years ago, a flood of gamma rays hit Earth after a supernova explosion. It may have caused the Ordovician-Silurian extinction, one of the most massive on the planet. The culprit of the catastrophe is assumed to have been in the near-Earth arm of the Milky Way. Its radiation destroyed half of the ozone layer and made about 85% of all living creatures go extinct. A supernova explosion is only dangerous for us if it happens no further than 50 light-years from Earth. Fortunately, no supernova candidates have yet been found among our neighboring stars. But there is still a chance a wandering star could pop out of some cosmic corner, ready to explode. Or maybe, somewhere in a secluded corner of the Milky Way, there's a dangerous star hiding from astronomers. So it would be a good idea to incorporate supernova detection into our planetary defense program as well. As our understanding of cosmic phenomena grows, so too does our awareness of the potential threats they pose to Earth and other celestial bodies in our solar system. From comets colliding with Jupiter to supernovae erupting in distant galaxies, each event offers valuable insights into the workings of the universe and underscores the importance of planetary defense strategies. One of the most intriguing yet potentially hazardous events in our cosmic neighborhood is the phenomenon of gamma-ray bursts, GRBs. These bursts are intense flashes of gamma rays originating from distant galaxies, marking the birth of black holes or the cataclysmic death throes of massive stars. GRBs are among the brightest electromagnetic events known in the universe, capable of releasing as much energy in a few seconds as our sun will emit over its entire lifespan. In October 2022, astronomers observed a notable gamma-ray burst designated as GRB 221009A, originating from a supernova in the constellation Sagitta, nearly 1.9 billion light-years away. This burst sent a wave of X-rays and gamma rays hurtling through space, detected by instruments like the Fermi and Swift space telescopes. Such events serve as reminders of the violent forces at play in the cosmos and the potential impact they could have if closer to Earth. Gamma-ray bursts are classified into two types: long-duration and short-duration bursts, each potentially indicative of different cosmic events. Long-duration bursts, lasting more than 2 seconds, are associated with the collapse of massive stars into black holes. Short-duration bursts, lasting less than 2 seconds, are believed to result from the merger of compact objects like neutron stars. The energy released during a gamma-ray burst is staggering. Fermi's observations of GRB 221009A detected gamma rays with energies exceeding 100 million electron volts, far surpassing the energy of visible light photons. The aftermath of these bursts, known as afterglows, can be observed across various wavelengths, providing crucial data for astronomers to study the physics of these extreme events. While GRB 221009A posed no direct threat to Earth due to its immense distance, the possibility of a closer gamma-ray burst remains a concern. In Earth's history, gamma-ray bursts may have played a role in past mass extinctions, such as the Ordovician-Silurian extinction event about 445 million years ago. This catastrophic event, linked to a GRB within the Milky Way's vicinity, is thought to have caused significant environmental disruptions, including a depletion of the ozone layer and widespread extinction of marine species. Understanding the potential effects of gamma-ray bursts on Earth requires ongoing research and monitoring. Modern space observatories, equipped with advanced detectors and telescopes, play a crucial role in detecting and studying these bursts. By studying their origins, frequencies, and potential impact scenarios, scientists can better assess the risks and develop strategies to mitigate potential threats from these cosmic phenomena. Beyond gamma-ray bursts, Another cosmic event of significant interest is the impact of asteroids and comets on planetary bodies. Earth, like other planets in our solar system, bears scars from past collisions with celestial objects. One of the most notable recent impacts occurred in March 2022 when asteroid 2022 EB5 entered Earth's atmosphere, captured by meteorological satellites. Although relatively small at only 2 meters wide, the event highlighted the ongoing need for planetary defense measures to safeguard against larger and potentially more destructive impacts. The study of asteroid and comet impacts is not only crucial for understanding planetary geology but also for assessing the risks posed to Earth. The frequency of near-Earth object, NEO, encounters underscores the importance of monitoring and tracking these objects to predict potential impacts accurately. NASA and other space agencies worldwide maintain programs dedicated to identifying and characterizing NEOs, focusing on objects that could pose a significant threat if they were to collide with Earth. In addition to monitoring and tracking NEOs, efforts are underway to develop technologies for deflecting potentially hazardous objects away from collision courses with Earth. Concepts such as kinetic impactors, gravity tractors, and nuclear deflection strategies have been proposed and studied to varying degrees. The successful redirection of the asteroid Dimorphos by NASA's DART mission in 2022 demonstrated the feasibility of kinetic impactors for altering the trajectory of an asteroid, offering a promising step forward in planetary defense capabilities. Furthermore, international collaboration in planetary defense initiatives continues to expand, with organizations like the European Space Agency, ESA, the Japan Aerospace Exploration Agency, JAXA, and others contributing expertise and resources to global efforts. These collaborations enhance our collective ability to detect, assess, and respond to potential asteroid and comet threats, thereby reducing the risk of catastrophic impacts on Earth. Looking beyond our immediate solar system, astronomers also study cosmic explosions and phenomena in distant galaxies. The Ophiuchus galaxy cluster, located approximately 390 million light-years from Earth, is home to one of the most powerful explosions ever recorded. This event, detected by multiple observatories including NASA's Chandra X-ray Observatory and ESA's XMM Newton, punched a cavity in the plasma cluster surrounding a black hole that is equivalent in size to 15 Milky Way galaxies placed end to end. The sheer magnitude of energy released during such cosmic events provides invaluable data for understanding the physics of galaxy clusters and the role of supermassive black holes in shaping their environments. By studying these extreme phenomena, astronomers gain insights into the evolution of galaxies, the dynamics of galaxy clusters, and the distribution of dark matter and dark energy on cosmic scales. In addition to cosmic explosions, the study of supernovae remains pivotal in astrophysics. Supernovae are stellar explosions marking the dramatic deaths of massive stars, culminating in the ejection of outer layers enriched with heavy elements into the interstellar medium. These explosions play a crucial role in the cosmic cycle of element production, seeding galaxies with elements essential for the formation of planets, stars, and life itself. Supernovae can occur through different mechanisms, including core collapse in massive stars and thermonuclear explosions in white dwarf stars in binary systems. Each type of supernova releases vast amounts of energy and radiation, contributing to the chemical enrichment of galaxies over cosmic timescales. The remnants of supernovae, such as nebulae and pulsars, serve as cosmic laboratories for studying the conditions preceding and following these explosive events. One of the fundamental questions in supernova research is the role these explosions play in the evolution of galaxies and the universe at large. By studying supernovae across various wavelengths, from radio waves to gamma rays, astronomers can trace their impact on galactic dynamics, star formation rates, and the dispersal of heavy elements essential for life. In conclusion, the study of cosmic explosions, gamma-ray bursts, supernovae, and asteroid impacts provides a window into the dynamic and often violent nature of the universe. These events, while rare on human timescales, have profound implications for the evolution of galaxies, the formation of planetary systems, and the potential threats posed to Earth. Continued advancements in observational astronomy, space exploration, and planetary defense technologies are essential for enhancing our understanding of cosmic phenomena and safeguarding our planet against future cosmic calamities.